Now we're continuing with states of matter, and we've really already talked about this, but just to reiterate, we've talked about gases as being, again, collections of atoms, and in this case, the kinetic energy of the atoms is going to outweigh the ability of the intermolecular forces, or is it intramolecular? In any case, the forces between the molecules. The kinetic energy is so high that the forces between the molecules don't have enough time to act or affect the gas, and they don't predominate anymore, and the molecules are free to move about completely on their own. And of course, those forces still exist when the molecules are colliding with each other. The forces act on the molecules, and that's why interesting things happen to gases when you change the temperature. Because, we'll talk about that more later. But in any case, in the gas, the intramolecular forces don't have much of an effect on what's happening with the gas, and so you've got these atoms or molecules just bouncing around freely. Now, let's say you continue heating up your gas, and you can do this in a number of ways. You can simply shoot higher energy particles at them, and then when they collide, the gases end up with very high energy. Sorry, making a mess here. So this high energy particle hits this, and then it goes whizzing away. So you've increased the temperature of your gas. You could do this with a flame, for example. You could also fire radiation at your gas, and the effect is always the same. The temperature goes up. So here's a very high energy photon. Here it is. Okay, and it's zooming in, and it's going to shake the gas, and so the energy, the kinetic energy, just gets higher and higher and higher, and you reach a certain point when the kinetic energy gets so high that when the atoms collide, the electrons, or some of the electrons of some of the atoms, begin to get stripped off. And then we have no longer in what we call a gas. We have reached the fourth state of matter. We are now a plasma. And I'll draw, here's our plasma. So let's look at our model of a plasma. We have your positive atomic nuclei, and I'm just drawing 1 plus. I mean, it depends on the atom. If it's hydrogen, it's just 1 nuclei. And then you've got your electrons whizzing around the outside. But because the kinetic energy is so high, some of these electrons have gotten stripped off and are floating freely with the gas, floating around, also with very high energies. So, a couple interesting things. An electric current can flow through the plasma. What does that mean? It simply means these electrons are free to move wherever they want. So, if you have an electric field, so let's say, and we'll learn more about this, so let's say we have one side of a battery here. I'll draw my battery. This could even be a car battery. And here's the other side. And so you have a positive plate here and a negative plate here. The electrons are going to flow and make their way towards the positive plate. And more electrons will come off of this negative plate, and you have your current now flowing through this substance. Well, where would this happen? Say you're welding. Well, that welding arc is a plasma. Say you have a neon or a fluorescent light, like the ones that are in your science lab. Those have plasmas in them. You might not think that those, and you're wondering, well, that light doesn't seem very hot to me. Well, that's because it's almost entirely evacuated of gas. There's just a few gas molecules in there, but when they are excited, and this time you're exciting them by an electric current, their kinetic energies are becoming extremely high, the electrons are getting stripped off, and indeed you have a plasma. So plasmas are conductive, meaning a current can flow through them. They are extremely hot. Their temperature is very high. However, if their density is low, meaning there's just not a lot of atoms in there, even though they have a very high temperature, when, in the case of a fluorescent light, only a few of those very high energy atoms are hitting the glass, so you don't end up feeling like the plasma is very hot. Anyway, that's a plasma, and they're found in many, many, many places. Let's make a list here of places where we would see plasmas, and interestingly, you see them much more than you might think. Let's take a look here. Where do we see plasmas? At least in our technologicalized society, we see them in fluorescent lighting. Fluorescent lights. Lightning. Of course, we don't see that in Kodiak. I think I spelled that wrong. I can't spell up close. I think I told you guys that. Oh, did something there. There, lightning. I know that's wrong too. Anyway, you see it in lightning, and you see it in anytime you see a spark as a plasma. But it turns out that the sun is also so hot that it is a plasma. So the sun is a plasma. And that's why if you've ever seen close-up pictures of the sun, you'll see those solar flares and they have those weird arcs and stuff. That's because the strong magnetic fields of the sun cause the electric currents that are flowing through the plasma to get bent around, and you end up with the sun being this electromagnetic thing. So, and it has all these strange shapes that are happening because it's a plasma. So if you take this into consideration, that the sun is a star and the star is a plasma, and when you look up at the night sky, almost everything you see is a star. So pretty much when you're looking up there, you're looking at balls of plasma. And the idea is that a plasma is basically a very high energy gas, and it conducts electricity. And so because it conducts electricity, it interacts very strongly with magnetic fields. And we'll learn about that when we do our section on electromagnetism. Magnetic fields will bend, twist, and affect plasmas in many different ways. The northern lights are plasmas. When you see the aurora borealis, which you do see here in Kodiak, so we don't get lightning, but we do get aurora sometimes. That's a plasma. That's protons from the sun impinging on the very rarefied or low pressure gas in the upper atmosphere, causing the electrons to get stripped off of the gas molecules, and you end up with a conductive gas. And as those electrons are falling back onto their respective atoms, photons of different colors are emitted, and you have the beautiful northern lights, which is an example of a plasma. So we have solids, liquids, gases, and plasmas. There are other very strange states of matter. They are not observed regularly. One of them is called the Einstein-Bose condensate, which is a weird quantum mechanical thing that happens only at extremely low temperatures and under very, very particular circumstances. And the other is a neutron star, which we just don't see. So anyway, Those are other states of matter that we don't need to worry about. You just need to worry about, generally speaking, in your everyday life, solids, gases, liquids, and plasmas. Now we will do a section on the gas laws, and that will conclude our lecture for this week.